So dew point and adiabatic saturation temperature. In that regard, we have got the sketch between the temperature and entropy. This is the curve. Now dew point, suppose if the air is at the point 1, so when the temperature is reduced, then what will happen? Suppose it is in the room, and in one of the room air is existing over there, temperature is reduced, so after some times we will reach from point 1 to point 3, line of the point 3, and it will just start touching the curve. Here it will be dpt, dew point temperature. Here it is dew point temperature. Okay, for saturated air the dBT, WBT and dpt are the same. Saturated air के लिए सब ये पॉइंट एक ही होता है. The adiabatic saturation temperature at which the air can be brought adiabatically to saturation state by the evaporation of the water into a flowing stream. So you can see that from point 1, when temperature is reduced, we are reaching at the point dpt, that is dew point temperature, and that temperature is reached when we go on reducing the temperature of the room or in any space. Another process of reaching to the saturated point, that is by injecting the water, from point 1, by injecting the water we can reach at this very point of the saturation point. So in two ways we are reaching the point. One is by reducing the temperature of the room, and another by saturating the water, applying the water on in the room and bringing the temperature down. Now this temperature which has been reduced from 1 to T2 temperature, this is what exactly happened in the desert coolers. In desert coolers, what is happening? That the temperature is getting reduced. Temperature get reduced with the help of flowing of the air over the stream of the water. Flowing the air with the stream of the water. So in that way we get the dew point temperature dpt, and another way of getting that temperature T2, that when we allow the air to pass through the water stream. Okay, now this was the curved between the temperature and entropy. Now this top point, this is known as the critical point. The left hand curve, this is your liquid curve. Right hand curve, this is vapor curve. So liquid curve and vapor curve, both the curve are intersecting over here at the top, and that is called the critical point. So in that way this is the curve between the temperature and entropy. Now practically how we do it, that let us analyze it. This is a closed vessel which has been shown over here. It is insulated from every side. Heat can neither can go out nor it can come in, both sides. Heat is being insulated, so it is no adiabatic action, no isothermal action, so it is completely insulated. Now this vessel is filled with the water. You see, the vessel is filled with the water, and this air is being charged at the point from the point 1, that unsaturated air, that is at the temperature T1, enthalpy H1, and a specific humidity omega 1. So this is the entrance air, and it is traveling over the water surface and taking the heat from the water surface, and then it is going out. When it is going out, then its temperature is T2, enthalpy is H2, and specific humidity, that is omega 2. Now this temperature T2 has been shown by the T star, and this is your adiabatic saturation temperature. Now when the water is getting evaporated from here, so we have to make up the water also from somewhere, because when as the air passes through this, energy of the air is being it discharged to the water, and water get evaporated. So there is transfer of energy from the air to water to get it evaporated, and to compensate the air water which is being consumed, we have got the makeup water system at point through at point 3, and here the temperature is T3, but this temperature should also be equal to the temperature of outlet air, so that a balance is being reached, and energy balance should reach inside the container. Now, concept of adiabatic saturation process. Now we will deal with the concept of the process. The process continues until the energy transfer from the air to the water equal to the energy required to vaporize the water. By this time the air reaches exit section, it becomes saturated, and an equilibrium reaches. The temperature of the exit air is called adiabatic saturation temperature, or the thermodynamic wet bulb temperature. In the starting I have shown you that we are going to deal with the adiabatic saturation temperature. So this temperature, the air which is coming out from the vessel, outlet of the vessel, that is your adiabatic saturation temperature. Now the air which is coming in contact with the water, it is imparting the energy to this water, and this water get evaporated, and that goes out, and we make up the water from the outside. The steady state thermal equilibrium condition are maintained by adding makeup water steadily at the rate of evaporation. Okay, this makeup water has to be at adiabatic saturation temperature, that is the temperature of the mixture, the exit air. Okay, adiabatic saturation temperature, the water which is being made up over from point 3, that should also be adiabatic saturation temperature, that is the temperature of T3 should be equal to the temperature of T2. The adiabatic saturation process is represented by the path 1 2. On the TS diagram if we go, then this path 1 to 2, 1 to 2, 1, upper 1 to 2, that is adiabatic saturation process. Means air is being forced through the water, and that water get evaporated, and air also get cooled down. So T1 to process 2, 1 to T2, this is the adiabatic saturation process. During adiabatic saturation process, the partial pressure of water increases, although the total pressure of the air vapor mixture remains constant. The outlet temperature T2 is T star. T star is the outlet temperature, adiabatic saturation temperature. For all practical purposes, the adiabatic saturation temperature is taken equal to wet bulb temperature. Adiabatic saturation temperature जो होता है वो wet bulb temperature हो जाता है जब हम उसको saturation state में जब पहुंच जाते हैं. The steady energy equation can be written as, अब energy का equation हम लिख रहे हैं. The steady energy equation, that is enthalpy at section 1, the air which is coming in, plus enthalpy at section 3, that the water which is being supplied over here, equal to the enthalpy at section 2. So this is the energy balance in enthalpy at section 1 plus enthalpy at section 3 equal to the enthalpy at section 2. Now what is the enthalpy at section 1? MA1, mass of the dry air, HA1 plus MV1 HV1 plus MF3 HF HF3 equal to Ma2HA2 plus MV2HV2. That is the equation number 1, where Ma and Mv mass of dry air and water vapor respectively, and Ha and Hv is specific enthalpy of the dry air and water vapor respectively, and Mf3 and Hf3 are mass and specific enthalpy of water added टू द मेकअप मास एंड जो वाटर हम अलग से ऐड कर रहे हैं ऊपर से, दैट इज MF3 एंड HF3. नाउ फर्दर मैथमेटिकल इक्वेशन वी विल गो फॉर द मैथमेटिकल इक्वेशन. सो फ्रॉम द principle of mass of conservation of energy, Ma1 is equal to Ma2 because the entrance air mass and Ma2 outlet air mass is the same, that is equal to Ma for the dry air. So Mv1 plus Mf3 is equal to Mv2. क्लियर फ्रॉम द फिगर से हम इसको देख सकते हैं कि हम अलग से वेपर का जो मास है जो इंट्रेंस एयर का है प्लस MF3 दैट इज़ द लिक्विड वेपर विच इज़ लिक्विड मास